Okay, so let's start with just something simple from that you guys would have done in Python. So let's say I wanted to have a loop that prints a string of text some number of times. Okay, nothing really super fancy. Um, so the old hello world. So what do I need? Huh? A loop of some sort. Okay, so if I want a loop, I need to do something like for I in range, let's say 0 to, I'll just print 10 times. And then what do I want to do? Print something, okay? All right, and let me save the file. Okay, and then if I run this, and the terminal should pop up down here at the bottom so we can see the output, then yay, what do we get? Hello world 10 times. Great. Now, in Python, right, this range operator 0 to 10, how did I know it was going to be 10 times and not 9 or 11 or whatever? Right. Okay, now that's the annoying part of the syntax in Python, right? Is the range operator or the range function that does starts at 0, the first number, and ends right before the last number. So the 10 is never the value of I, right? It takes the values 0 through 9. Now, I think the reason that Python did it this way is because if I start at 0 and I go to 10, it's really that I have 10 things, not that I'm stopping at 10, right? Because I end up at 9. Um, that's mildly annoying, but we just got used to it, okay? And then the other stuff that we've got, right? What did we sometimes have to do in a Python program up at the top before we had really any code? We had to import stuff. Okay, now in this case, I don't need to import anything, but we maybe needed to import the math libraries or some of the stuff to do, fancy things, graphics or whatever. And that's going to be true also in C or even to some extent in assembly, right? Is that we're not going to literally write every single thing completely and utterly from scratch. In the same way that here, how did it print? Did I write the print function? No, somebody else wrote that. That's part of Python's built in library. C, likewise, has got printing kind of functions in it. And we just made use of an existing part of the language by calling it here. Now, we can create our own functions, and we certainly will do that. And you certainly did this when you were in Python. Okay, but there are some built in functions like printing or getting user input or something like that where we're just going to call something that already exists in the library. Okay. Um, okay. Now the other stuff, right? In Python, how do you know what the body of this for loop is? The indentation. That's it, right? In C, you don't have to indent anything. Now, the practice of good programmers in C is to indent. Okay, but the nesting and what is inside of what is all handled with curly braces. Well, so when Python was being designed, sort of thought, well, everybody indents everything anyway, so why don't we just make the indenting the whole thing? Seems logical, right? It also means that Python code's a little neater to read than C, but it's also a newer language by 20 something years. Yeah. Right. And so in Python, and so when Thomas says he means Guido van Rossum, the guy who designed Python in the first place, and that was in the early '90s that he was working on this. Um, and whereas C as a language goes all the way back to the '70s, and even further if you sort of trace its predecessor languages, You'll be shocked to know that guess what one of the predecessors of the language C is? B. Yeah, I know, right? Um, so no, but there was Algol. So, but there was no language called A. So yeah. Um, okay. So right. So in Python, right, we had lots of constructions for doing things like iterating. We had a for loop. We had conditionals. We had the ability to access files and start processing information that was contained within them. Uh, we were able to take user input, do user output. We could do math, all of those sorts of things. We want to look at, well, how do you do all of that in C? Okay, so let's write essentially this same program, or actually we'll just print it once to start, but in C. Okay, so let me save it. Okay, so, and then it wants to install the extensions, which I already thought I had done, but apparently not. So we'll let it do that. Um, so that'll just take a second. Um, oops. Okay, so I need to include standard input output, the header files. This basically gets me the printing functions and stuff. And then I also, so this is something that Python doesn't make you do, although some of you, at least that had 111 with me, you remember that we would sometimes have a main function that was essentially the entire program, and then we would just call the main function, maybe a little bit. Um, so in C, you have to have a function called main. And typically it starts this way. Okay, and I'm going to try and get in the habit of putting the curly braces like this. Okay, so what does this mean, int main void? So this means that main is a function, and all C programs have to have a function called main. That function can call other functions that are going to be where the guts of the program is, but there has to be something called main. Now, the int and the void part. So if we think about a function in Python, right, the function can be kind of whatever you want, but what is a function at all anyway? Like what, or maybe let me back up. What's a function in math class? Yeah, you give it a thing, a mathematical object, and it returns some other mathematical object. Okay, you can have functions that take 20 variables and spit back one thing. You can spit back 20 things if you think of it as a vector of 20, as one thing that's built of 20, right? So a function takes stuff in and spits stuff out. Does a function actually have to take stuff in, though, in a computer sense? No. So in math, um, at least the math that you guys have seen, we never have functions that take in no values. But we could think of there being one. It's just they're not useful in most mathematical contexts. Where you would do this in, okay, I'll deal with all that later. Where you would do this in, say, Python is, let's say, for example, you had a routine to make a sandwich. And let's say that routine is, place down piece of bread, put peanut butter on it, place down another piece of bread, put jelly on it, and then put the two things together, right? And if you called that function make sandwich, does it really have any inputs? Well, okay, yeah, maybe you could say it has the input of the bread and the peanut butter and the jelly. Okay, but let's just say, right, we in that case we can use a function as just a shorthand. So saying make sandwich, that one instruction really means 5 instructions: bread, peanut butter, bread, jelly, smush. Okay, so there's not really any inputs or outputs in that sense. Okay, does that idea kind of okay? All right, now in C, functions don't have to take in inputs and they don't have to return outputs. They can. Okay, and when you declare a function, though, you have to specify explicitly what's coming in and what's going out, or rather, what data types are coming in and what data types are going out. Okay, so if I have a function that takes in nothing and returns an integer, then when I define that function, I have to define it as int, that's the type of thing that's being returned from the function. Main is the name of the function. And void, in this case, is signifying that it's not actually taking anything in. Okay. If I wanted it to take in an integer or some other data type, I would have to put that where the void is, and we'll talk about that later. Okay. All right. So why does main need to return an integer even though I'm just going to print hello world? Well, yeah, it's the way you specify the type, and it's also a convention. Right. Okay. So we're operating here under Linux, right, which is an operating system. Like I said, most of you, with the exception of Isaac, has anybody used Linux before? Okay. The nerds. Okay. Um, well, I'm offended you haven't used Linux. Right. And what is the +5 on you?
Oh, sarcasm.
Oh, okay. He's got a +5 of sarcasm. Yeah. Yeah. You know, I'm going to walk in one day and you're going to have like a bunch of Munchkin cards. You know, you know, yeah. Um, okay, so sorry, where was I? Return value. Okay, so within Linux, um, and Windows doesn't have this exact scheme, but it has something sort of similar. When you run a program, you're not running a program on a sort of bare computer. We haven't been running things that way since essentially the early 80s in terms of the PC or personal computer world. So um, what I mean by that is like if I run this program, I mean I haven't it's not done yet obviously, so nothing's going to happen, but if I run this program, I'm not running it sort of on its own. I'm really running it in the presence of an operating system, in this case, Linux, right? And Linux is going to handle a lot of stuff like loading it off of the disk and putting it in memory and making sure that I don't break Linux in the process, right? So there's a lot of stuff happening behind the scenes. And one of the conventions is that your program should return an integer to indicate to both you and the operating system under what conditions did it terminate. This is called an exit status. And the convention is exit status 0 means everything went okay. You can use this for debugging, right? So like let's say that your program exits at some point and it's exit status of 1, well then that can tell you where you exited because you're the one who puts the exit number someplace. Okay. So that's why we need to return an integer, even though it doesn't really seem like we need to. All right. So what I'll do is let's do, say, something like this. Okay, so the two things that I needed are, well, I want to print something, so I need a function to print it. And there are actually multiple functions that can do this. The one that I'll use, at least for this instance, is called printf. The F stands for formatted text. And then I'm going to return the value 0 back to the operating system, basically just to say, yep, everything went cool. Okay, now, in addition to, how do I know what's inside the function main? It's whatever is in this pair of curly braces. I do not have to tab over everything that's inside the curly braces. However, is it a good idea to do so? Yes, because it makes your code more readable. Okay? So this is why Guido adopted that practice and just got rid of the curly braces part. Because, and this, by the way, is why you never program at 3 in the morning, because you will never find that missing curly brace at 3 in the morning. Okay, or missing semicolon for that matter. Um, a habit that you guys are going to have to get into, and it will take a little bit. You'll screw it up. Um, is that every instruction has to end with a semicolon. You did not have to do that in Python. You're going to forget a semicolon, and it's not going to work. Just it'll happen. Okay. All right. Now, if I want to run this, what do? Well, this is where things get a little bit different compared to Python, right? If I run a Python program, really what I'm doing is passing the Python code to another program called the interpreter. And the interpreter is what actually runs it sort of on the fly. That's not the case with C. Okay, so if I want to run this program, what I first have to do, oops, sorry, let me see if I can. Let me blow up the text in the terminal. Where is it? Well, okay, of course it's not obvious there. All right, I'll configure this later, but so it's a little small at the moment, but just bear with me. So what I have to do is I have to compile this. Okay, so what compiling means is I have code. This code right here is just a text file. That's it. Now, yes, it has certain formatting and certain symbols and whatnot, and we interpret this as code, but as far as we're concerned, this is just a pile of text. How do I take that and turn it into actually something that the machine is going to run? Well, I have to turn it from a text file into a bunch of ones and zeros that are actually instructions. Okay. And so to do that, I use a program called a compiler. Now, when you're running Python, you're not doing this. Python is sort of running it on the fly for you. Python's an interpreted language. C is not. So what I need to do is I need to compile it using a program called GCC. Yeah, Thomas. It is. Okay. So yes, and which is one reason it's so fast. Okay, because C is fast. So when you load a program into Python, its interpreter is sort of on the fly converting stuff to C or interpreting it and running it. But it's not, you're not compiling it in the same way. Now you can compile it, but yeah. Okay. So I need to use GCC. That's G stands for GNU. And then, so this is the GNU C compiler. And I need to tell it, well, what input file do I want to give it? It's hello1.c. And I need to do -o to specify what my output file is. And in this case, the output file is, I'll just call it hello1. Okay. Now, nothing, no errors, no spit back, everything was good, right? And so now I can see that there's this file here, which I can't actually view. Well, I sort of can. Okay. So all of this gibberish, okay, is the program. This is actually what gets executed. Um, and it looks like gibberish, right? It's just a bunch of stuff in hex. And over on the right, the hex values are being decoded to ASCII. In particular, and this is actually kind of neat, what's the very first thing we see? Yeah, it actually is ELF, not ELF is in the fictional race. But yeah, so on Linux, when you compile something, it compiles into a format called ELF, which is like, what does it stand for again? Like extensible linkable format, something like that. Um, anyway, basically just means it's a Linux executable. Okay, so you can hand this to a Linux operating system and it'll execute it. So all of this gibberish, right, are actual machine instructions that tell the processor do this, do this, do this, do this, and the sum total of all of that is going to be what? It's going to spit out hello world. Okay, but the compiler was the program that took in our code and spit out that executable format. Okay, now let's run the executable format. Okay, so what's the name of the program? Hello one. All right, so all I have to do is try type hello one, right? Nope. Under Linux, how do you run a command that's not part of the operating system? You have to do. Oh, I've already done that part. I've already done the compiling, right? Now I want to actually execute the program. So I need to do dot slash hello one, and that will actually run it. Okay, that's a Linux specific thing. If you were on Windows for this, or well, yeah, on Windows, on Mac, Mac operating system works very much like Linux because they both are descendant from Unix. So yeah. Ah, okay. Good thing. Good note. So you see how it says base next to each line of stuff? That actually has to do with my terminal, and all of your terminals are going to do the same thing. So what happened is when I printed something in Python, it gave me a new line at the end of it. That was not the case with the print function in C. So if I want to have it go to a new line at the end of that printing, then what I have to do is put backslash n. Okay, backslash n is um, the escape code for a new line, right? And now I just changed the code. So what do I have to do? Do everything all over again. Recompile and re-execute. Okay, and now it does have the carriage return. Okay, so the base there was not part of the string. It just was part of the terminal, the terminal down there at the bottom. Now, this base thing, what that's for is actually, since you guys are all have done this, um, so in Python, right, you need to have packages installed, right? And what kind of packages should we use in 111? Yeah, we use some of the image libraries. We use the turtle library. We use the Pygame thing at the very end, right? We used a bunch of packages, right? Well, what happens if you're working on two different projects and one of them uses version one of Pygame and another one needs to use version two of Pygame? What do you do? Huh? Yeah. So you can't have two different versions of the same package installed simultaneously. So what you do is set up virtual environments, okay? And you have one virtual environment that has version one of the thing and a completely separate virtual environment that has the other thing. And a program that helps you manage this is called Conda. And Conda is appending to the name of the terminal here which environment is currently running, which, because I haven't set any Python stuff up on this, is just the base default environment. If I wanted to create a bunch more environments, then I could switch which one is active at any moment, and Python will use the one that's currently active. So that base thing, you can just ignore it unless you're doing a bunch of Python stuff. Okay, good? All right, so let's actually dive a little bit more under the hood as to what's actually happening. Okay, so this compiler it took all of this code, right, and spit out something that's executable. But it didn't do that in one swell swoop. It looks like it did, right? Because I only typed one command, but really two things happened. All right, so let me type different different command, and this has produced a new file called hello1.s. Okay, so if I look at this, this is just a bunch of text, right? But it's also code. It looks like code. Well, what the hell language is that? Huh? This is assembly. Okay. So assembly is lower level than something like C. I mean, if you look at this, like, does it look like what we wrote at all? Not yet to you guys. It will later. Okay. And what are these instructions like move BL? I mean, you guys can probably guess what the add command does. That's not rocket science, but um, right. All of this is, as far as things go right now, kind of gibberish. Right? So when you're compiling code, what really is going to happen, and this happens all in the background, so you don't have to worry about it most of the time, is your C code is turned into assembly by one program. That's called the assembler, or sorry, the compiler. You now have assembly, and that needs to get turned into machine code that the processor actually can execute. That's done by an assembler. What we're going to do after a few weeks of doing C is instead of writing things in C, we will write stuff directly in assembly and bypass the compiler step altogether. Okay. In doing so, we'll really start to understand how the processor really functions and how code runs on a machine. Now, the reason that assembly is a useful thing is because there is a one-to-one correspondence between every single line of this code, okay? Well, the ones that don't start with a dot, which I'll explain what all those mean later. So like this BL puts or move W0, comma 0, right? That corresponds directly to a machine instruction, and that move W0, comma 0 will translate into a 32-bit machine instruction. And on this processor, every instruction is 32 bits, period, end of statement. So the assembler is the thing that does that translation. But what's nice is every line of assembly corresponds exactly to one 32-bit instruction, one to one. That's not true about C code, right? We wrote that loop that printed and returned, right? And look how many instructions it actually took to accomplish that. So what looked to us like 2 instructions is really 1, 2, 3, 4, 5, 6, 7, 8. Okay. So why is it that we like something like C better? It's easier, right? It's higher level. Okay, and what I mean by high level is we're more abstracted away from the computer, from the hardware. Okay, assembly is lower level in that we're closer to the actual chip in the language it speaks. Now, so here's one other thing about the C. If I took that exact same program and ran it on a PC, right? Same C code, and I compile it, the compiled program that I run, is it going to be different than the compiled program on my Raspberry Pi? The compiled version, yes. Are they going to both do the same thing, namely print something? Yeah, okay. But, so C, like Python, right, does it matter what computer you run Python on? Not really, no. You got a Raspberry Pi, you got a Mac, you got Windows, who cares, right? I could give you all the exact same Python program and you could run it and it would run and everything would be fine. Okay. With C, you're still kind of thinking of the computer as a black box, but maybe not quite as maybe there's like a glass window on the side of one of the sides, right? You can see a little bit, but it's like tinted glass or something. You know that there's some stuff inside, but you can't really see all of the exact details there. When we're programming an assembly, that's like a glass box instead of a black box. We can literally see all of the different parts inside. Okay, so like I said, and the whole point here is we'll use C as kind of this glue, if you will, to transition you guys from high level, like Python, to starting to think in more low level terms in, say, assembly. Okay. Now, this assembly, by the way, this is 64-bit ARM assembly. If I were to compile this program on my PC and look at this resulting stuff, it would look very different. The reason, uh, processor in my PC is, yeah, different. It's an x86 architecture, right? So Intel AMD, versus this, what's in the Raspberry Pi is ARM architecture. Okay, it's like French and Spanish, right? They're different languages. There's similarities, but they're not the same exact thing. And actually, maybe with ARM and x86, it maybe should be more something like, oh, I don't know, French and Russian, right? Like if you go back far enough, there's probably a whole bunch of stuff in Proto-Indo-European that's ended up in both of them. But like, is there really much mutually intelligible between French and Russian? Not really, right? Now you could point and say, okay, well, this French word is the equivalent of that Russian word, and for a lot of things, but the language structures themselves are also quite a bit different. Um, yeah. So, I mean, it's not a perfect analogy, but this kind of what I'm, yeah, it's not a perfect analogy. Now, one of the reasons that I like the ARM architecture, at least for the purposes of teaching, is the 64-bit ARM architecture is a little over 10 years old. It's essentially a clean sheet architecture. All right, now let's take the Intel architecture. If I take my machine and I turn it on and I hit the power button, it starts in one mode. And that mode is 16-bit real mode. Now, when the heck were we using 16-bit computers? Yeah, none of you were alive then. This is when I get to be the old professor. And, you know, back in my day when we had to walk uphill both ways in the snow and we liked it. Right?
6 months, but yes, that's not possible.
Yeah. So the Intel, the 8086 or 8088 processor, okay, or really the 8080, these are processors that were from the 70s, 1970s. Okay, what did computing look like in the 1970s? Well, yeah, definitely using punch cards, but the personal computer space, the microcomputer space, right? So IBM, the first PC, used an 8080 processor, or 8086 actually, right? And it was a 16-bit processor, right? So what is the limitate? Like, who cares about how many bits a processor is? So when we say 16 bits, what do we mean about a processor? Yeah. So all data, like integers, numbers, would be encoded in 16-bit. Okay. Now, 16 bits is a lot in some sense and not a lot in another sense. So, in fact, what's the largest integer you can encode with 16 bits? Right. Well, 65,535 because you need to also encode zero. Okay, so 65,000, oh, it's not actually all that big, is it? Right? Now, if you can do 16 bits, you can do more. You just have to do it in sort of separate stages in the same way that, like, when you guys are in kindergarten, you learn how to do single digit arithmetic. And then later you learn how to do multi-digit arithmetic. And what is multi-digit arithmetic other than just single digit arithmetic repeated over and over? Right? And you guys just learn that, right? So you can do the same sort of thing with a computer. Um, but maybe the other way to think about this is what a computer needs to have memory, yes? It's got to load instructions into memory. It has to process things in memory. How much memory does it have? Back in the 70s, how much memory did computers have? Yeah, kilobytes worth. Okay. Kilobytes. How many of you guys have ever used a floppy disk? Right? Yeah. Oh, you 3D printed the save icon. Right? I've heard that one before. Yeah. Yeah. So who's never used a floppy disk? Huh? You've never used a flop? Have you ever used the floppy floppies or just the rigid ones? Ah, yeah. Okay. That's getting old school, right? So the back when we were using those kinds of things, the the computers had on the order of kilobytes of memory. Nowadays, how much do they have? Well, of RAM, not of hard drive. Gigabytes, right? So the Raspberry, our laptops, they have 8 gigabytes of RAM. Uh, a PC, like my PC at home, is 64 gigabytes of RAM. That's about the most you can get in a consumer product. All right. But back in the day, they had way, way less than that. And the original IBM PC could support up to, if memory serves, it was 640 kilobytes. Right. This is where we get the famous Bill Gates quote, 640K ought to be enough for anybody. I think it's 640. Fact check me. Um, I mean, I am getting old. So, um, okay. So the Intel architecture that was used in the IBM PC. So what starts to happen in the 80s, right? So early 80s. Let's see. Can I have that like in writing? Yeah. Okay. Yes, exactly. Um, what started happening in the 80s, right, is memory. Well, it's kind of like today, right? So how many of you guys bought an iPhone, say, 4 or 5 years ago? How much memory was on it? Storage. Just we'll use storage and memory interchangeable for this discussion. Yeah, 64, 128 gigs, somewhere around there, right? All right. If I wanted to go buy an iPhone today, how much storage would it be able to come with? Yeah, maybe the base one is 128 or whatever. Now, when the original iPhone came out in 2007, how much RAM or how much storage did it come with? 4 or 8. There were both models, right? So last year's iPhone, or maybe let's say 3 years ago's iPhone, maybe was $1,000 and came with 32 gigabytes. And this year's iPhone is $1,000 and comes with, say, 128 gigabytes. So why is that? What happened there? So it needs more space, okay, but why is it the same price? Yeah, we're producing more and more of it, and we're getting better at packing more and more of it onto a chip, which means we can fit more of it into a phone, and it's cheaper because we're producing just gargantuan quantities of this stuff. Okay, so the same thing was happening in the 80s, right? RAM was becoming less and less expensive, and programs, operating systems were becoming more and more sophisticated and needing more storage space and more memory. So um, the Intel architecture got to the point where, all right, it's a 16-bit machine. Well, what's the next frontier? Let's do 32 bits, right? Well, then you have a problem because what happens if you now have a 32-bit processor, but you've got all this code that other people have written for the last year's version that's all 16-bit? They have to make them redo all of their shit just so that their code can run again? So what did Intel do? Yeah, they made it so that it could still run old stuff. They added the 32-bit stuff on top, which is good, but also bad. It's good because your shit still runs. Well, maybe not so much slower, but it means that your architecture is kind of turning into a Frankenstein's monster. Okay, because you just keep tacking crap on top of more crap, right? And this happened in the early development of the x86 architecture, right? The 8086, okay, great, and then the 186, and we won't talk about that. And then there was the 286, and we added some stuff, and then the 386, and the 486, and then the Pentium. Oh, I remember when those came out, right? And we just keep tacking more and more and more shit on top, and eventually, like I said, it turns into Frankenstein's monster. All right, now Intel tried to do a clean sheet thing in the I think early 2000s. It was called Itanium. It was a train wreck. And this is why actually the 64-bit stuff that's on Intel AMD chips was actually done by AMD. And Intel, they cross-license back and forth, which is how they keep from suing each other into oblivion. Um, okay, so the Intel architecture uh, has retained backwards compatibility. And so what that means is that some of the machine instructions and things, you look at them, and to fully understand them, you have to go back and think about what would computers look like in the 70s. Okay, and that's kind of weird. ARM is, or at least the 64-bit ARM, was clean sheet, meaning there's no backwards compatibility, right? Let's design a new thing from scratch. And as such, there's not the baggage going all the way back to the 1970s, which I think is maybe a good thing, at least for teaching purposes. Um, yeah. Okay. That's probably a good place to quit. So is this kind of making sense? All right, let me show you one other thing, or two other things. So, what are you all going to do this morning? Yes, go get your computer from Jill. And actually, yeah. Now, the other thing is under Linux, right? You have the little folders. You can find stuff. So I put stuff, where did I put those documents? Oh, here it is in this folder here, right? So I've got files. I can make them into a list. If I wanted to turn in this program to Dr. McKinney, how would I do it? Okay, yeah, you need to zip it all up. All right, now a zip file, what is that? Yeah, you're combining a bunch of files, and you can do that very easily. If I wanted to zip all of these together, I would just select them and hit compress, and bam, it would say, okay, what do I want to call my archive? And I'd say it's, let's say, assignment1.zip. Okay, now the archive type, um, if you guys just do zip, that's fine. There are a bunch of other ones like tar, gzip, etc. Those are, you don't have to worry about the differences, but tar is pretty standard, so I'll just do that. So, oh, did I hit cancel by mistake? I think I did. Anyway, that's how you do it. Okay. And the last thing would be on Canvas. Um, there are a couple of instructions that you need to follow in order to do the very initial setup of your Pi. Okay, so if you go to our Canvas page, you will see Raspberry Pi initial setup. Okay, there are these are the instructions that you need to go through to get it set up, and in particular, to get it associated with the Wabash IoT network. So the Pis cannot connect to Eduroam because of the authentication protocol is they can't do enterprise authentication, but they can do connect to Wabash IoT. And so as such, you have to register them. And I've deliberately not registered any of y'all, so you'll each register them. The link that you need is right there. Okay. And then there's a few other things just to make sure that you can actually get it connected, get into Canvas, and start kind of fiddling with it. Okay. All right. Good. All right. See you guys later.